Good morning and welcome to the ALCF developer session for April 2020. I'm Ray Loy. For those of you who don't know me, I'm the ALCF lead for training and a member of the ALCF performance engineering team. This webinar series was created to foster discussion between the software and hardware developers and early users of the technology. Today's topic is software deployment with Spack, and we're pleased to have with us Frank Wilmore from ALCF. Frank started out as a chemical engineer and went on to the research staff at the Texas Advanced Computing Center. He's the lead editor and contributing author to Introduction to Scientific and Technical Computing from the CRC Press. And at ALCF, he's part of the operations team where he works to facilitate the development and deployment of scientific codes on our leadership computers. And I'll add that Frank is taking the lead in Spack deployment at ALCF, as you can tell from the title. So with that, I'll turn it over to Frank.
All right, thank you, Roy, for the introduction, and thank you, everybody, for tuning in this morning. Again, I'm Frank Wilmore. I'm software integration admin at working within operations at the ALCF, and talking about deploying software with Spack and a little bit about how we are approaching this at ALCF. So I'll start off to talk a bit about software deployment more generally. When we have software to install, whether it's to our laptop, or to a virtual machine, whatever setting where we need to run something, there's typically I'm doing this from the command line, and depending on what OS you're running, you could be running Yum, RPM, other package managers. You could be downloading tarballs, configure, CMake, and then make install with those. But typically, that's for small scale systems. Well, we also have to do this for large scale systems, large shared systems, which I force the additional complications of being multi-user, multi-architecture, and specialized hardware as well. For example, Summit here. So how do you install software to a supercomputer? Well, you can download all the tarballs you need, start building. You end up editing configuration files, editing some system files, hoping you don't break something else. You might update something you really don't want to update because you need to, and you hope that doesn't break anything else. And then you may have to re-edit whatever settings you may have changed for your dependencies, and you may consult your notes from the last time you tried to install the package. You end up pestering a colleague. You say, like, how do I do this? How did we do this before? And ultimately, and you hope that the software version wasn't changed without bumping the version number and giving you a loss of information that way. And hopefully you can get through this process. You may end up running your code and then having it segment faulting and having to start all over. So we're looking for a more robust solution for software deployment. Additionally, let's say that it's safe to say that software complexity and number of dependencies and the linking between the dependencies is only growing. For example, this code for generalized unstructured massively parallel low Mach flow. Deal 2 is yet more complicated, and we see R minor with it's getting to look just plain scary in terms of numbers of dependencies and things that you need to actually have functioning and coordinating correctly within a built software environment. So what's the solution? What about modules? Well, most supercomputers deploy some sort of environment module program, whether it's the Tickle modules or LMOD, and these allow you to manipulate your environment. For example, you need to load a certain set of compilers, a certain set of things, and they're very good for that. But what they're not doing is installing anything. They're just changing your environment so that you're getting the things that you need based on what's already installed. And you're able to module load a number of things. And this is de facto way that people generally deploy or generally put an interface for users on the supercomputers through module system. All right, so what about containers as a way for deploying software? Well, containers, they're also a great way to reproduce and distribute an already built software stack. The promise of containers is that you can have your layer of abstraction at the kernel level, and you can actually run whatever OS you want as long as the Linux kernel is new enough. In reality, though, when you're running on a supercomputer, for example, on ours, we don't support that layer of abstraction. We support it at the MPI layer, where you can interface to Craze MPitch through the application binary interface. So it's higher up the stack. And still, with containers, it's you still need to deploy the software within the container. Somebody still needs to do that, which again is not trivial. And customized applications can still have hundreds of dependencies. You don't actually gain anything just by having it in containers, other than a certain amount of portability, subject to the caveats above. But building in containers does offer a couple of additional complications as well. Some of these being that if you're building for a container, you're generally not optimizing for the architecture that you're going to be running on. If you're building a container to run only with Haswell instructions, you're not getting the vector, like AVX512 vectorization, that you need to really reap the benefits of high-performance hardware like KNLs. So you end up with the lowest common denominator for your binaries, just for the sake of portability. And if you're developing within a container and you're only developing against the provided OS software stack, like if you're in a Red Hat container, then you're only using the pieces that they're providing for you, then it's going to be painful. You're not going to have control over the versions you need, the options you want for all of the packages. So we would like to have something more flexible in order to build the containers and to do software in general. This is the goal of SPAC. This is kind of where SPAC comes in. And to say in a nutshell what it is, SPAC is a package manager, not unlike RPM or Brew, which allows you to automate the deployment of software. The caveat that it allows you to deploy multiple versions of a given software package, built for different architectures, different numbered versions, and built with different options with different build options. Basically multiplexing for, I'd like to say, every possible combination. It allows you to build and deploy those simultaneously on a given system. It's supported under Exascale Computing Project, and it's the package management tool of choice for this project. And installations are ranged from large HPC to individuals working on laptops. For example, you could actually build something on your laptop with SPAC to get all the components that you're used to having on an HPC system. You might be able to get that and do that work on your laptop before scaling up to an HPC system. Potential benefit of SPAC as well. Now, installing SPAC itself is fairly simple and straightforward. It's a Python. It's written in Python. It doesn't require any compilation as such. You can install it simply by cloning SPAC itself from the GitHub repository, and then you're running you source a shell script which gives you tab completion and just makes SPAC generally easier to use. And I'd like to mention just at this point, one thing that's really handy with SPAC is the tab completion. And if you're not sure, if you have some familiarity with SPAC and you're not sure what command you need to use, hit SPAC and then hit tab. You write SPAC and then hit tab. It'll show you the different options. And then if you need to find out what more of those options, then you can say help on whichever one of those options. So in real time, that's a real handy way to get some help because SPAC is very complicated and there's a lot of documentation, but it's not always easiest to get out to the documentation when you're actually actively working with it. That said, installing a package can be as straightforward as saying SPAC install, for example, HDF5. And what this will do is that it will find HDF5 and its dependencies, and will download the pieces that it needs, and will build all the dependencies as well as HDF5 within the SPAC directory. It's within the SPAC installation. There's an opt directory that can be configured for your system, but that's by default it goes into the SPAC the SPAC installation itself. And again, it can install variants of the same build using different compilers, using different MPI implementations, and different build options. And target audience is for SPAC. I kind of divide this up into about 4 groups, where one is the domain scientists and end users of HPC. So they may, for example, you may have a physicist or a chemical engineer wants to build lamps and run it, and before they're scaling up, they can actually install a version of lamps using SPAC and get the dependencies built on their laptop or in their home directory or in some simple way before they go for scaling up and really leveraging the full hardware of a large scale system. So the end users, other people is application teams, people who are building the applications for those users, the lamps developers, for example. Going further down the stack, it's pack developers, maybe people who are building packages and make available. For example, HDF5 common library has a SPAC package, and it's easy enough to use SPAC to install it. And then finally, the 4th group is people like me, the system administrators who are tasked with installing and supporting installations of software at large HPC sites like ALCF and on our Theta system. And so it's a useful tool for us. Okay. To speak a little bit about how SPAC works, when you ask SPAC to do something, you provide what's called a spec. Now, this is, for example, to install MPI leaks package, could be HDF5, but if you just give it an unconstrained spec, SPAC will figure out the rest of it for you. It will make some decisions for you, and we'll get into that in a bit. There are things that you can specify, some constraints that you can add. Let's say you want to build at a particular version, you want to build with using a particular compiler, you want to build with a particular option, for example, throwing in the threads option, which is something that SPAC will understand based on what information SPAC has about that package. You can add compiler flags, and you can add a target architecture. Again, many systems are moving toward multiple architectures, so it's important to be able to target for the specific CPU so that you're able to get the cycles out of it that you want. And you can also include you can explicitly include dependencies. You could say, let's build this using a particular MPI or a particular MPICH, and you want the MPICH to be built a certain way as well. That you can have these cascading dependencies that you can specify. And excuse me. And you can customize these on the command line as you're installing. There's other ways to specify this, but you can do it on the command line. And again, the syntax is recursive. What you specify for compilers, it will build the whole stack with. So you get, more or less, you can get full control over the combinatorial build space. There are currently over 3,900 packages in SPAC. Depending on what you have, what package repositories you have installed, these may or may not all show up. This is just an example of showing a subset of those. You can find out what you have actually, so SPAC list tells you what's possible to install. SPAC find tells you what's actually installed on your system. So for example, running SPAC find, you'll see a number of packages installed under particular operating system and architecture, and then with a particular compiler here. These are what's installed that way. This is showing with a different compiler version. This is with the Intel compilers. There's some old versions here. This is some older material. But you can see all of the things that SPAC has installed. And again, you can see that you're able to install more than one version of a given package. Now, something SPAC does in order to make these different versions work is that it will actually it will find its dependencies at runtime. It uses RPath for the link, tells the linker to RPath in paths to where it finds dependent libraries that it's built on. So you can You can use module system. SPEC will also generate modules. What's notable here is you can use the SPEC modules as such to help specify things when you're installing, but you don't have to have the module system set up correctly at runtime. And also, SPEC will provide modules, either LMOD or Tickle modules, but you don't have to use them. It will generate them, but you don't have to use them. And you may need to edit them by hand depending on what your system configuration looks like. I know NERSC does a fair amount of editing their modules by hand. I've done some work just to curate and pick out certain versions of things which make sense to put to expose more broadly by linking into the module system. That's another thing on how we have deployed ours. Now, you can also ask SPAC to find or to tell you all of the dependencies for a given package. For example, this is looking at a particular package call path is installed. Tells you which versions there are, but you can dig deeper and it will tell you all the dependencies. You'll see the expressions at the left being these hashes, and we'll talk a little bit more about that as we get on. But that's what distinguishes the different versions more than simply just the version numbers and the names of the package. And again, note that you can distinguish between different versions for different builds of things. This is, like for example, this one's built with Clang and using Boost 159. This one's built with GCC using Boost 155. It allows you to do those to do those different dependencies. Now, from the viewpoint of a packager, you have to tell SPAC what your software project needs, and the way that this is done is through what's called a package.py file. And in this example, we're just declaring a base package, and we're saying that it's going to inherit from a CMake package. So it's going to be like this has got a CMake build system, so we're just going to inherit CMake's CMake specs infrastructure for using a CMake package. You can include metadata in here, like your home page and your URL, hashes to verify different versions of the software, variants that are available, and dependencies. And because this is written in Python, you have all of Python at your disposal when you want to clarify what these dependencies are, or how you want to make how you want to declare any of these things. And you can specify some arguments, and you can declare an install process if needed. If you don't declare these things, it will inherit the ones from CMake package and or whichever type, or if it's a make file package, whatever the underlying build system is. It'll do some things like that automatically, but then it allows you to put this layer of customization on top of that. Another thing SPEC allows is for virtual dependencies. And in SPEC, as a good example of this, MPI is a virtual dependency. You can declare a package to depend on MPI without having to say it depends on MPISH or OpenMPI. You can just say it depends on MPI. And then when you're actually building it, you can tell it which one you want to use. If you don't tell it which one to use, SPEC will pick something for you. It may or may not be what you want. So it's important to look at what things that SPEC gives you before when you spec something, you can see what it's going to give you, and then you can actually go ahead and build it if it makes sense. Otherwise, you may constrain it further. Okay, for a given piece of software, there's a dependency graph, and for example, this MPI leaks program has 5 dependencies. When you're building this, it takes these dependencies and it takes the versions of those and it turns those into a hash, as I mentioned before, to distinguish them by the version and by what other dependencies are being rolled into that particular build of the software. And I mentioned before, SPEC embeds RPAS in the binaries, and it allows you to, which means that you can build packages. You can build software using SPEC built products. You can and you can get the right products in your environment using the modules. but you don't necessarily need to have those modules loaded at runtime because, or then you don't need to have them in your LD library path at runtime because SPAC is including RPAS when it builds the binaries themselves. So things work the way you build them. A caveat to this is that it means that SPAC, it means that you can't relocate those dependencies. You may be able to relocate your binaries, but if they're depending on it, if they have RPAS for dependencies, then those are not trivial to relocate. You either have to edit the ELF files or just rebuild them, depending on those needs. Okay. So again, this is just hashing all the components get thrown into this hash for each of the versions that's built. So this process of fleshing out the rest of the spec based on what you tell SPAC to build, like for example, we're telling it MPI leaks with this particular call path, with this particular option, and to use this particular dependency for libelf. There's this component of SPAC called the concretizer, which actually fleshes all these out in terms of exactly what compiler, exactly what options are being specified, et cetera, et cetera. And this is what actually gets built by SPAC and during its install process. So you have a fully concretized spec. And this is what gets installed. It's notable that the concretizer can sometimes give you surprising results, and there are ways to put some constraints to the concretizer. There's work being done to develop a new concretizer, but it's unclear exactly when the new version of that will be released, or how much different that will be. It's still unknown at this point. There are some ways to tame the concretizer with environments, and I'll get to that in a bit. There's something called environments, which allows you to more tightly constrain what's being concretized, what information the concretizer is using in determining which dependencies are getting built. This information goes into a file just called spack.yaml. You can put it in a particular directory, and that will be considered an environment. Then when you tell it to install, it will, based on what's in the SPAC YAML file, it will figure out the dependencies, and it will generate, concretization will generate this lock file where you can see what exact versions there are that are installed. Because it's being done with an environment, this is going to override other levels of system settings. One of the issues with SPAC is it has six different places where you can set scope for its settings, and where it will inherit settings from. And the concretizer takes all of these settings from all these different locations into account when it's determining how it's going to build something or how it's going to flesh out its satisfiability requirements. So again, environments is a way of taming that process a bit. It's also a way where you can deploy a particular environment for users. If you want users to be able to only see certain views of everything that's installed in SPAC, you can create an environment for that. That's actually a pretty handy thing to do, and it's similar to what's done with some other environment types of environment management tools, like some of the Python tools for virtual environments. All right. To move on, we'll talk a little bit about some of the newer features in SPAC 014X versions. These were released in February of this year. Lots of new features. SPAC has many features, possibly ad nauseum. I say that because it makes SPAC difficult to learn. But nevertheless, there are a lot of great and powerful features in SPAC, and more coming in all the time. Of particular note is the SPAC CI generation command, where you can generate GitLab CI files from your SPAC installation automatically based on any changes that you've made to an environment. I'll speak a little bit more to that. Other features that are included now are recipes for building or being able to build containers directly from environments. There's a containerize command, which allows you to build out a container based on an environment. And also there's support for distributed or parallel builds. It's and this is handled. It's a Slurm command executed there, but this could be an app run or just being logged in different shells and running more than one Spack install command. Spack will doesn't step on itself now. It'll actually manage locks using file system locks to make sure that it's not stepping on other processes working in the same space. So the newer features are building on some existing 0.13 features. Some of these include Spack stacks, which allows you to declare an entire environment for facility and deployment, and some better support for specific microarchitectures, as well as chaining, in which you're able to declare an upstream Spack instance where you can build against packages that are in another Spack instance. It's smart enough to recognize, like, oh, there's another Spack out there that has a lot of what I need. And this is currently the recommended way of interfacing with our Spack instance at ALCF, is to use it as an upstream, for some reasons I'll get into. Now, speaking to processors, it can be challenging to figure out what your processor is sometimes. You can ask proc CPU info on Linux or system control on a Mac, and you get a lot of information back. But unless you're really a chip head, this may not be especially helpful. Humans call this architecture Broadwell, so that's something that's easier to put your head around or to work with, is to say, oh, we need to build a Broadwell version of something. Okay. Spack understands these microarchitectures, and it can actually allow you to do some comparisons of them. You can query Spack about what instruction sets are supported on architectures, et cetera, et cetera. So then you can actually use these. You can have, based on what Spack is able to ascertain about a processor, you can have your package ask if a particular instruction set is supported on the target architecture from within your package. So that can be really handy. So this example here, it says, like, if AVX 512 is in the supported architectures for that target, then we go ahead and put with AVX 5112 when we're building the package. Another thing that's come out of this, and I'll just mention briefly, is a standalone library, which allows you to make some of these architectural inquiries. It's been factored out of Spack, so it's just to let you know that exists. It can be handy. I wanted to share an example from a project that worked on at ALCF on the topic of multiple architectures. For example, our JLSE, it's an experimental environment at the laboratory for different hardware, for newer hardware. You can actually have the same Spack instance installed to all these different architectures from within the same setting, and they don't step on each other at all. And this is just kind of handy because you can factor settings, you can share settings, and it's just worth mentioning that Spack ended up being the easiest way for me to get a set of dependencies built when I was trying to do just to test out the HDF5 Deos connector on some new hardware on a different system. Yeah, Spack ended up being a really handy way to get those dependencies built. This is a really busy graph just to say that Spack now supports parallel builds. It's a flow chart just saying how it manages locks. But the point being is that you can have multiple Spack processes running against the same installation, building things, and Spack will make sure that it doesn't step on each other's process. The containerized command is again where you specify an environment here, and you can tell it some container settings. For example, what format you want it to be, a Docker container, Singularity container, whether you want to strip the binaries, some other options as well. And Spack will build this environment and put it in a container, and it can generate Singularity. Again, it can generate Singularity recipes or Docker files depending on what you're asking it for. and coming to SPAC stacks. You will often hear in the SPAC world, you'll often hear stack and environment used interchangeably. A stack is one thing you can include in an environment. A stack is basically a set of packages that you want to build according to a certain set of combinatorial rules. For example, what's now supported is specifying a set of compilers that you want to use, a set of MPI versions that you want to use, and a set of packages, and then generating a Cartesian product of these lists and with using this matrix imperative in the spec.yaml, the environment file, which basically says to build this stack, build the Cartesian product of these dependencies, and then you go out and you can specify how you want to build modules, etc. But it's the idea is that you can declare an entire stack for your facility, and that SPEC will just go and build it. This is experimental. SPEC is still a version 0 program, but this is where it's headed, what it's trying to do this and to automate this. And for some simple cases, this is actually fairly easy to see. Even some modestly complicated cases, you can do this type of behavior. Another thing that's new is SPAC pipelines. And what I can say about this is that if you've declared, for example, you've declared a facility stack. It's a specification of everything you want to build at your facility. And let's say you want to make a change to that. The SPAC pipelines are just a really crazy high level of next level of automation where you make a change to your system spec. That change triggers CI, which has SPAC go and generate a bunch of CI jobs for things that need to be built or rebuilt based on the changes that you've made. And this CI will go ahead and build and launch jobs appropriately, and to go ahead and build out all of those packages that you need. So you change the declaration of your system stack, and SPAC will with using GitLab CI will automatically rebuild and update your system deployment based on this. I'm trying to figure out how to pun on the word pipe dream. It's the dream of what we would like to be able to see done. It's an ambitious goal, but it's not beyond possibility. And there's always going to be things that need to be tweaked along the way to make sure that the process works. But there are prototypes of this. We've put together, we've implemented just a simple one, a very stripped down version of it on ALCF. And I've said most of this already, but basically you're declaring a stack. You can declare a mirror where you want to have packages, versions of packages cached, and you can actually have publish the progress of this build process to a C- dashboard as you go, if you so choose. This is developed by Kitware. C- is a Kitware product, and so of course they're interested in showing off their product. But it's possible to have a dashboard looking at the builds in progress using this workflow, SPAC CI workflow. So when you do this on GitLab, just as an example, it'll set up, like, you declare your stack, you push it up to your GitLab or to your repo on GitLab with CI kicks in, and it will generate based on what SPAC will generate all the jobs for packages it needs to build, and it'll generate them in the order that they need to happen based on cascading dependencies. So you have stage 0, stage 1, etc., where it will go ahead and build out all those dependencies. And anytime you make a change, again, it will reevaluate and give you those dependencies again. And this is just a screenshot from the prototype we put together here. Now we see a failing job in stage 0, and then it not moving on to the next stage. But we were able to get it as far as SPAC generating the job, or being able to define and generate the jobs it needed, but we haven't debugged individual builds of those yet. So again, it's the kind of thing where there's always going to be little things that break along the way, and that would need attention. But This is the concept of it, though. You'd have this pipeline to generate based on just declaring a spec for your entire stack. And again, speaking again to some of the vision for SPAC is that we'd have automated building of packages from the various E6 labs based on public and private package repositories, and SPAC users would be able to get easy access to these packages, and they would not have to build their own software for high performance computing necessarily. A lot of it would be automated, and that's the dream. That's kind of the SPAC dream and where it wants to go. It's a challenge. There's many challenges along the way, but it's good to know the direction. There's some information here if you're interested in engaging with the SPAC community. A few things I want to mention. The SPAC documentation is definitely good and worth reading. The community itself is really responsive. There's a Slack channel. There's you can open bug reports. You can interface on GitHub with SPAC as well. It's what you're looking for. You can find. There's just, if anything, there's too much information and it can be a lot to get around. But don't let that hold you back. It's a useful tool. Okay, last section here is just to speak briefly about what we have in terms of SPAC at ALCF. Software deployment existing software deployments at ALCF are on ALCF data are through a number of mechanisms. One of them being the image, which is a read-only file system that's mounted on every compute node. This is basically a set of RPMs that get knocked down to and distributed as a single SquashFS image. Certain things have to get put in there. For example, singularity has to be put in there because you can't deploy that on shared file system because set UID requirements. So it's a security risk to put that in. Like for example, soft. Soft is a Lustre file system mounted on all the compute and also the service nodes. And a lot of software gets deployed here. A lot of people have access to it. It's kind of the Wild West. A lot of entropy, just for people to be able to share packages and such there. Another place for installation is Theta Archive. This is a place where we store older versions of compilers as well as builds of packages which were formerly supported but perhaps not explicitly supported anywhere. They're not actively in the image. Things that we've pulled out of the image to go into this archive here. We have a module system for interfacing to the software environment. There's Python has its own ecosystem. We have a couple of supported versions of Python at least. A couple. I say a couple. There's like at least an Intel plus another. I think there's a Miniconda install that are supported. And then finally, the topic here is we have a SPAC deployment which is becoming increasingly relevant. This is also deployed under our Lustre file system. So it's a shared file system, and so you can't put set UID things in there. But most of the software, or a great many of packages, can be supported through that mechanism. PowerPoint hanging up again. Okay. All right. So, and current ECP efforts with SPAC for this and the next quarter are the SPAC pipelines, which I mentioned, with the whole CI workflow for generating automated deployments. Integration with the vendor stack is a topic that we're looking at this quarter for how do we interface with the Cray software stack and Cray and Intel software stacks in particular. We're onboarding projects in CI that are in need of that. Kyle is kind of our go-to person, is our go-to person for that, for projects trying to get into CI on our systems. We're beginning to look at integrating container deployments and trying to figure out what that's going to look like on our systems. And there's just ongoing deployment efforts with SPAC as well. And I'll share current vision or the current thinking of how the SPAC installation at ALCF is designed to work. We have on the left here we have those using SPAC to build codes. This can really include all users either using the system directly or as an upstream SPAC repository where they're able to build against what's already installed there for their dependencies. Packagers can use this when they're packaging software. It's another class of users, people who are packaging software. The build pipeline would be an automated interface into that, so you can have CI deployments building directly against the system, the central SPAC installation. Users who are members of the software group can deploy directly into this installation. We don't open this up to anybody on the system, but it's a trusted group of people who are allowed to deploy software, and it's based on an existing group called the software group who typically was doing that in soft anyway. There's a SPAC service user who owns the installation itself, and there's a set of tests that we run to make sure that the installation is set up correctly and it's still functioning correctly. Those run as the SPAC user plus a dummy user for testing out the multi-user functionality of it. And of course, CI service users that are interfacing to this as well. The product of this is a set of deployed software within that SPAC instance. Again, SPAC can build nearly unlimited combinations of software. We don't want to be able to see all those. We don't want to know about all those or worry about all those. So we have for the average user, there's a set of curated software that's available, and these are just handpicked out of there and symlinked into basically a view into this system installation. This system installation is kept in sync with SPAC and kept updated against against the most recent versions of SPAC. It can be set up to point to pre-built binaries. Like if there are other sites that are building for the same architecture, we could be sharing binaries with them, provided that they're trusted and we have mechanisms for trusting. And then also for interfacing with, for example, the vendor stack for MPISH, compilers, etc., and as well as just system software. We have this instance of SPAC working against those external dependencies as well. It's all built on top of a user group owner permission model. It's all owned by a service user, and it allows it to be incorporated using upstream SPAC installations. And this is currently the recommended way due to some shortcomings in the way SPAC currently handles multi-user. Some current issues that SPAC has with the multi-user install. And this is all, again, managed with environment modules, or you can manage your interface into it with environment modules for the average user. So the last thing to talk about is some of the challenges that we've seen arise with the multi-user installation of this type. There's issues with SPAC itself. The learning curve and inherent complexity of SPAC are the rewards of SPAC are real, but they do come at a cost. It's considerable learning curve, but there are benefits at the end of that. Specifically for multi-user SPAC, some of the challenges though are with incompatible builds. Not every combination works, and your package PI files may get out of sync, or may not be maintained by the users or by the publishers of them, and they may not be aware of bad combinations, and so builds can break. Packages whose build systems don't support cross-compilation, HDF5 is one that falls into that. It needs to build, its configured process builds a particular code which it uses to determine, I can't remember if it was the value of a macro or the size of a type. It was something like that, where it actually runs that where it's being built, and that breaks cross-compilation for that particular package. Let's see, missing or out-of-date package files. This is SPAC's chicken and egg problem. For SPAC to work, it needs everybody to use it, but for everybody to use it, it needs to work. So that's an ongoing challenge. But a lot of packages. There's 3,900 plus packages available now in SPAC. Obviously, some of those are going to be better maintained than others, but there's a lot of buy-in now at that level. So that questionable choices by the concretizer based on what's already been built and what's available and settings, etc. Again, a new concretizer is coming, and hopefully it will solve some of those problems. Some builds can require disruptive updates to some of the system packages, and it might need a different version of OpenSSL, but we don't want to change out the OpenSSL version because security. So some packages just have picky dependencies that are not easy to satisfy, and especially if it's an external package. And conversely, vendor updates can require settings for some of these external dependencies. Vendors vendors will have their own way of packaging things, and they don't necessarily have the same philosophy about how things are versioned or controlled, etc. And so those can be a little bit challenging. Generally not terrible, but those can be challenging. Conflicting settings or confusing settings. I mentioned 6 levels of configuration scope, plus stacks and environments, etc. Those are messy. There's a Spack blame command to figure out where it's getting settings from, but that's really useful, and if we can figure out how to not make it pick up certain settings, it's a challenge. Sometimes there's dependencies on. So software publishers are not always. They're not necessarily going to have Spack as their primary concern, and I've seen dependencies on a unreleased software version. For example, in building SDK, it declared a dependency on a version of adl.c, which I don't know if it exists now, but at the time it didn't yet exist. And the way to get around it was to use develop, but develop is not a fixed version of something. And as someone with a scientific background, the idea of a control variable is near and dear to me, and version number for me is a control variable. You should not have a floating version of something that you're calling particular version number. That's I think only bad things can come from that. And then there's some bugs I've mentioned that manifest in the multi-user version. Spack in its operation, it will rewrite some of its own files. And sometimes I've noticed issues where it's rewriting those with different ownerships or with different group write permissions, and I'm starting to enumerate some of those bugs and report those. But it causes things like when somebody else tries to use the multi-user Spack installation, who should have privilege to use it through the software group, they will often not have privilege to edit a file or to read a file, or usually it's write permission on a particular file, or else it'll have the wrong group ownership. So again, I'm starting to enumerate some of those issues, and some other minor issues. Not all dependencies are sponsored by ECP. ECP has a big hammer that they can swing to try to make a lot of these things work together. But not every dependency further down the stack is sponsored by ECP and may not have an interest in making it work especially well with Spack. It's not anything malicious. It's just there's not resources to make it work the way it's supposed to. And of course, non-semantic or unusual versioning systems. Spack does pretty well to support those, but they can make it a little bit confusing. Spack can infer how to build something based on version numbers. It can actually, even though nobody's told it explicitly how to build the latest version of CMake, it's actually smart enough to figure out how to build that just because the version numbering is it's done in a consistent way that it already knows it's basically able to infer how to do that. Which is pretty cool. I was surprised to see it build a new version of CMake that it didn't have a specific entry for in the package file. And something happens just in practice is that and probably for many of the reasons that I've mentioned, is that other users of the system, either because it's cumbersome to work with the system install, to interface with it because of the bugs, or they end up just cloning their own version of Spack anyway, because then they have complete control over it, which is understandable, and which is why I'm recommending using the system install as an upstream repo, which means you can basically get the benefit of it without having to have the headache of it per se. So That said, SPEC is a useful tool. The rewards come with effort, but my experience is it's certainly worth putting in the effort. So with that, I thank everyone for attending, and if there's any time left or anyone's interested in questions, we've over the time a bit here. So SPEC uses the matrix special. Yes, SPEC to just clarify. Yes, SPEC uses the matrix specification in an environment. The stack can include a matrix, and it can also include other packages as well. Matrix is just a shorthand for writing out the Cartesian product. You set it to text your current architecture, but what about cross-compiling? So you can tell it which architecture to build for explicitly. There's you can specify that like a target equals, for example, Linux /12 x86 64. If you want to build, like for example, on Theta, the default is to build for the KNLs. But if you specify target equals x86, wait, is it Linux /12 x86 64? If you specify that as your target, then you can force it to build for the for that architecture for the login nodes. GitLab CI runners are the system. Oh, hold on. The GitLab CI runners are the systems nodes where the packages will be installed. Used. You can again, SPEC supports multiple architectures, so you can build packages that you want to use on the system nodes, and you can also build packages that you want to use on compute nodes. Sometimes you run into errors, into troubles with the cross compilation for the things I've mentioned, and you end up having to build packages you want. If you want to build packages for the compute nodes, you may end up having to build them there. Alfred says, if I understand it correctly, SPEC is a general purpose installer. Most users just carry about a few software packages for their own applications. They don't really care about other packages. Is it worth the effort to learn SPEC for most users? That's a really good question, and honestly, it's learn it as much as you need to. I would say it's for most users. It's a bitter pill to swallow, but it's also a really useful tool. So use it as much as it's useful. And the other thing to note is it is getting better. The documentation is good, and it is getting better with time. But yeah, that's really a tough, can be a really tough call to make, whether it's worth the effort.
I think just I agree. Let me just add that I think it kind of depends on, even if your application only depends on a few packages, there may be multiple builds of those. You often find yourself in the situation where you need to build with the same things, but the underlying libraries maybe have different options, and managing that becomes a headache. And then you may have your own build options, multiple ones as well. So there could be, even in a fairly simple case, a good argument to use it, but it really depends on your situation.
Yeah. I will add, learning SPEC in a multi-architecture environment is an additional challenge. And just from my own experience, I'd learned SPEC on Theta, and I was always running into the multi-architecture issue made it harder to learn. So if you have a smaller setting, or like a VM or something, that might be or on your own laptop or something, it might be an easier setting to learn it in. That's just from having been through that. Okay, we have Tom Brown's asking, what type of optimization does SPEC do and does not do? SPEC doesn't do anything explicitly. It passes information to the build system. So if the build system knows how to do that, or knows what optimizations to do, and if the SPEC package knows how to communicate that to the build system, then SPEC can pass that information to the build system. That's in a nutshell how it happens. SPEC, you provide a way. The package file provides a way for SPEC to get information to the build system, and the build system would know how to do the optimization. Okay. Let's see, we got Leon Grindino. Can you explain .spec folder that has some logs commands used for build? Yeah, so this is one of the configuration scopes. There's a hidden folder in your home directory it's called .spec, and you can specify settings there. Really, I have to refer to the documentation just to say look at the excuse me, look for configuration scope in the user documentation to see how those settings are handled. There also are logs there for if you're building as a regular user. You can look through there and see logs about how SPAC is building, and that's so you can get some information there. See why it's failing because it happens often enough that's worth looking into. That SPAC folder. Okay, and then from Jacob, is asking, when using an upstream, I find it can be a challenge to get SPAC to generate the same hashes. And I have found that I need to copy the packages.yaml file and compilers.yaml from the upstream. Is this the recommended way to use the upstream? Yeah, okay, another good question. I'm as a maintainer for ALCF Spec, I'm moving away from having settings in the installation itself and I'm in favor of moving these settings to a separate location where Spack doesn't automatically pick them up. Partly because those settings can be confusing to the concretizer and therefore to the person using Spack. So I'm looking at pulling those out. In terms of getting the same hashes, if anything at all is different, if there's some you'd really have to make sure absolutely every detail is the same to get the same hash. So I can't really account for why without knowing exactly which setting is getting picked up or what subtle version or dependency or option is off. That will change the hash, and it's to drill down and to see where it's coming from. But it's but I take your note, and I'm looking for a better way to optimize this as an upstream repository, and taking a step back from using it as a true multi-user installation the way it was intended. So this is a work in progress, as is Spack itself, and we definitely appreciate feedback, and I encourage feedback too. I put my email in the presentation, wilmore@anl.gov. Okay. And we have a note from Todd says, Todd, who's the Mr. Spack, head of the project, says, new concretizer will help with this and aggressively reuse hashes. Anything else, or if not, I'd just say thanks again for tuning in.
Okay, thank you, Frank, for the presentation, and thank everyone attending. As Frank was saying, we welcome feedback. You can also send that directly to devsessions@alcf.anl.gov. If you have any requests for future topics, we're all ears. And with that, I will conclude today's session.